So good evening, everyone. Thank you for joining us and welcome to our Geology Beneath the Waves webinar. My name is Andrew Finlayson. I'm a geologist here at the British Geological Survey in the marine geoscience. And the aim of the webinar tonight is to illustrate some of the work that we've been carrying out in the marine geoscience program with a focus on two priority areas in BGS's new strategy. So these being maps and models for the 21st century and supporting a more secure energy transition. So we've got three presentations lined up for you tonight, following of which we'll have a question and answer session. So if you do have any questions, please type them into the Q&A window. In the first talk, I'll give an overview of our UK seabed geology mapping programme. Gareth Carter will be our second speaker, and he's going to tell us about how understanding seafloor geology and developing ground models provides us vital support to the offshore renewable energy industry. And our third speaker will be Heather Stewart, who's going to describe a really interesting new research programme exploring seascapes in the deepest reaches of the world's oceans. So I shall kick off now with our first talk, which will be on mapping seabed geology around the UK. And the aim of this talk is really just to set the scene for a new mapping programme that we've just started in the marine geoscience team, and it's be the first systematic mapping that we've really done of the UK continental shelf in around 25 years. So I'll just spend the next 10 to 15 minutes chatting about that. So I thought it would be useful to start off by looking at why do we need seabed geology maps? And I can think of lots of good reasons for this, but I just want to flag a few key ones here. And firstly, and really importantly for our transition to net zero, is that planning for renewable infrastructure in the seabed requires knowledge of the geology. So the composition of the seabed is important for turbine foundations, for anchors, if that's either for tidal schemes or for floating wind, or if we're going to be planning subsea cable routes, or port expansion as well, because we'll need to expand the capacity in the ports as well. So this is something that Gareth can speak a little bit more later on. We also want to know where the seabed may be subject to geohazards. So the example in the bottom image here is of a coastal landslide in North Yorkshire, which is extended out onto the seabed. But we also have examples of these sort of processes affecting completely underwater areas. So here's an example on the top right image with underwater landslides in Loch Lomond. And obviously these kind of processes pose a potential risk to infrastructure. So we want to know areas that might be susceptible. We can do that through our mapping. We also need to know where our resources are. So 20% of sand and gravel that we use in our building industry, construction industry, it's met by marine aggregates. So a few more reasons here. Blue carbon, we want to identify, map and protect carbon-rich marine sediments, just in the same way as we want to lock up carbon in our peat bogs onshore. So the example image here in the top left is of a sea loch in Western Scotland. And we know that sea lochs can be hotspots for storage of organic carbon that's been sourced from the surrounding catchments. So we want to know where those are and map the formations in them. We also have habitats. So the geology and geomorphology of the seabed is a key influence on ecosystems. So understanding the distribution of the geology and geomorphology can help us understand different habitat types. And then finally, geoconservation. So we're getting more and more new data sets that are revealing really outstanding geological heritage offshore. The example in the image on the right is of the Bristol Channel, where you can see this really beautiful folding and faults and fractures within the bedrock that's been scoured by tidal currents. And we've also got the course of the River Severn from a period when sea level was much lower than today, so showing through that. So we want to be thinking about these kind of landscapes and preserving these landscapes, protecting these landscapes when we're thinking about management of the marine environment. So fortunately, for our mapping, we're not starting from scratch when we're looking at these issues. There's a huge amount of really valuable existing data that's already been produced. Between the 1970s and 1990s, BGS undertook a programme to produce 250,000 scale maps of the UK continental shelf. And these were based on bathymetric charts, thousands of kilometres of seismic data, and a program of seabed sampling and shallow coring. And we have an example, so image here in the bottom right, showing the BGS fibre core about to be deployed. And these would have retrieved sort of 6 metre long cores from the seabed. And these maps and data sets, they're a really valuable resource to us now, and they will continue to be a really valuable resource for us going forward. And importantly, they have full coverage of the UK continental shelf. And these data sets, they've been used to form the basis of some derived continental shelf maps that we've produced. So, for example, we have on the left-hand side a seabed sediment map for the UK continental shelf. The map in the middle is the depth to bedrock map. It can also be thought, for those of you that are going to know about the quaternary deposits, so we've thought a thickness of quaternary map. And then the map on the right-hand side is a bedrock summary. And these maps, along with several others, are available to view on our offshore GeoIndex. So we have the web address for that there at the bottom. Don't worry about copying it down, because these can be sent out with information after the webinar. So with that in mind, why do we want to start a new mapping program now? Well, we do have a growing need for more detailed seabed geology information. And some of the issues that we talked about at the start, things like marine planning, where we're going to site renewable infrastructure, where we're going to plan for cable routes, and also thinking about what we need to know about for seabed hazards and processes, they all really require detail that is beyond the scale of our existing maps. But fortunately, at the same time, we're getting lots and lots of new high-resolution data becoming available. So new high-resolution multi-beam bathymetry, where you have these fan-shaped pulses of sound that are used to map the shape of the seafloor, is becoming increasingly available around the UK. So this image on the bottom is how, an example of that data being collected in the offshore environment, from a larger vessel, but we can also use smaller boats to collect that kind of data in the nearshore and coastal environments. And here's one of our team, Reese, collecting that kind of data just earlier this month in a wee bit sunnier climates out in the Ascension Island. But that's how that kind of data is collected. And for our purposes, for the UK seabed geology mapping, we're relying quite heavily on the Civil Hydrography Programme data set that's collected by Marine Coast Guard Agency and the UK Hydrographic Office. We also are seeing more data sharing initiatives, which is really good for making this data available and used by different organisations. So, for example, BGS, we're part of the UK Centre for Seabed Mapping, which is promoting sharing of this kind of data. And as well as new data becoming available, we're also evolving our knowledge. So our scientific understanding of the landscape of the UK seabed is evolving, which we can really use to build that into our new mapping programme. And I will touch a little bit more on that now. So during the last ice age, global sea level was about 120 meters lower than today, and that exposed large parts of the UK continental shelf. And at that time, northern Britain and Ireland were covered by an ice sheet that reached about 1 kilometre in thickness, and that expanded out onto the continental shelf towards the continental shelf edge. And we can see this reconstruction here from about 26,000 years ago. That kind of depicts what that ice sheet would have looked like. And that's come from the really excellent Brit Ice Chrono project. So we have this amazing preserved glacial landscape on the UK continental shelf. We can see all these kind of moraines which form at the edge of ice sheets and subglacial meltwater channels, and lots of landforms and sediments that are derived from that ice age. And that's important because these are now the materials on the seabed that we're interacting with when we're thinking about management of the marine environment and developing and building on that marine landscape. So I'll just build on this now with an example from Anglesey, or offshore Anglesey, just in North Wales. So the image on the right-hand side is some of the multi-beam data from the CHP surveys, giving this really beautiful image of the seabed. And the lighter colours are where the seabed is shallower, and the darker colours are where the seabed is deeper. And in this image, you can see in the bottom left corner, you can see where bedrock is exposed at the seabed surface. We can see fractures and structure in the bedrock. Superimposed in that, we've got these really nice elongate landforms called drumlins, and drumlins form underneath ice sheets and glaciers. I've got an example image from Google Earth on the left-hand side here from Mullajökull Glacier in central Iceland, where we can actually see drumlins forming today. They're being exposed by the retreating Mullajökull Glacier. So the ones in the Irish Sea, they're in the right-hand image, these would have formed underneath the Irish Sea glacier during the sort of maximum stages of the last British ice sheet. Then that ice sheet began to collapse, began to melt back, and we had icebergs, sea level rose, and we had icebergs calving off the front of the glacier, ploughing these grooves into the seabed. And these are called iceberg plough marks, and we can see those in the center of the image. And we see the exact same landforms forming in front of active calving glaciers today in places like Greenland and Antarctica. And then fast forward to the present day, and we've got these ridges migrating across the seabed. So these are sediment waves, and that's part of the current kind of marine conditions in this area that are moving these mobile sediments across the seafloor. So we piece all this information together, and we're using that information, that understanding, to help us make new maps, which we want to be meaningful to a variety of users. So here is an example of our map, one of the maps from offshore Anglesey. And then we can see in this, we've got we've mapped out different substrates, so that's important for understanding different habitat types. We've mapped out these features, glacier moraines. So they're important because the sediment contained within them, the soils within them, are likely to be variable. We might have boulders present within those. And if you're thinking about foundations for wind turbines or trenching for cables, you're going to want to know that those are there. Fracturing and faults of the seabed, that's important for anchoring. If you're anchoring tidal schemes or anchoring floating wind turbines. Bedding ridges within the bedrock, so that could be important for, you may get spanning of cables across a seabed, where the cable's actually suspended above the seabed floor, which you want to avoid. Different sediment and bedrock types, that's important for, again, for foundations and cable routes. I've talked about the iceberg plough marks, so they're just really nice examples of our Ice Age history and the subglacial landscape, which is an important part of our geoheritage and our geodiversity, and the science of understanding how the ice sheet collapsed. Then we also see these mobile sediment waves, and they're important because we want to know where these features might be moving across the seabed, because they can affect cable burial and the thickness of sediments on top of cables, which affects the thermal performance of the cables. So I just want to touch now on how the new mapping kind of differs from existing data that's already available, existing maps that we've released that are already available. And I'll use the offshore Yorkshire area as an example and extract from the new offshore Yorkshire mapping. So in the top image, you can see the existing 1 to 250,000 scale digital bedrock map. We don't have too much detail in that. And then the central image, you can see the new fine scale seabed geology mapping, and you can see how the new data sets is really allowing a lot more detail in the interpretation. And here we've got folded and faulted Triassic mudstones alongside seabed sediments that's moving along the seabed. So if you're applying, for example, a cable route through this area, we'd hope that the new mapping provides a much more useful kind of baseline, or looking at an environmental impact assessment in this area. So just a quick slide now on where to find these maps. They can be found at our GeoIndex again, so that's the web address. And if you look in the table of contents on the GeoIndex, on the left-hand side, you scroll down through all the different maps that are available. You get to a layer of fine scale maps, and we've got a new Anglesey map, Bristol Channel map, offshore Yorkshire, Dorset, and we'll be continuing to add to that list of maps over the coming months and years. So where have we covered mapping so far? The areas in the green are where maps have been released. So these are available now. The areas in yellow are where the mapping is in progress. So we will be looking to release the East Anglia map, offshore East Anglia map, sometimes either side of Christmas. The extended Bristol Channel map, extending further out, will come shortly after that, and then the work later on early next year. The areas in blue are areas we've got mapping planned over the next couple of years. And then the areas in red are where civil hydrography programme bathymetry data is available. And that's areas that we will look to cover with this mapping over the next 5 to 10 years. At the moment, we're sort of prioritising the choice of mapping areas. It's guided by the availability of high resolution bathymetry data. Also, the need to develop regional geology knowledge to support kind of stakeholder needs. And also the science, what are the science drivers? And one of those at the moment is understanding the ice sheet processes, but we're also looking at kind of modern seabed processes. These are the areas we've chosen to now, but we welcome feedback on the areas that we should be prioritizing. So if you do have any thoughts on that, then please do feel free to use the Q&A tab and add in some comments there. If you'd like a wee bit more information about this mapping, the recent article in Geoscientist magazine in the summer edition provides a lot more information and detail to this mapping program. So just a few key points on the new mapping program. We've seen that there's new requirements for detailed seabed geology information. Thinking about infrastructure planning. We want to understand marine geohazards better. Thinking about marine conservation and geoconservation. At the same time, there's lots more high-resolution bathymetry datasets becoming available now. For example, chiefly through the Civil Hydrography program. And we have this growing scientific understanding of how our seabed has evolved through lots of ongoing research in the UK research community. Yeah, for example, ice sheet processes. So it makes it a really good time to combine all these developments together, and it puts us in a great position to start generating these new modern high-resolution maps of the seabed. And as I mentioned, these are available to view on the GeoIndex, and we very much welcome feedback on what people think of those and any ways that we can build on them or improve them. So yeah, happy to hear feedback there. So that's it from me just now. I'll stop sharing my screen and I will invite Gareth Carter, who's going to start the next talk on renewable infrastructure.
Brilliant. Thanks, Andrew. I will just share my screen now. Hopefully that is working for everyone. I'll pop that up too. Okay, yeah, so thanks, Andrew. My name is Gareth Carter, and I'm a marine geoscientist with the BGS. And for the next 10 to 15 minutes, I'll be describing the role the marine geoscientists play in the energy transition, and I'll primarily be focusing on offshore wind. So Andrew's given us a really nice overview of seabed mapping on the continental shelf, and we're going to stay there now, but what we're going to do is we're going to think about what is lying beneath that seabed in the upper 50 to 100 meters, because that's the zone of interest for these offshore renewable developments. And then once I've finished after 10 to 15 minutes, we'll slide off the continental shelf and we'll go down to the depths of the abyssal plain, and Heather's going to give us a really fascinating talk on the work that BGS is doing with deep sea mapping. So as we've already had from Andrew, a really nice overview of the type of map we can see here to the left, which is a top-down view looking down on top of the seabed. And you're going to have to bear with me just for 1 or 2 slides on this analogy. But now if we imagine looking down on the top of a cake, we would see, a very topographic relief all over the top of that cake, very bumpy, but we want to know what that cake looks like inside. So what happens if we take a knife and we cut a slice of that cake and we remove it? And so as you can see, our example here on the left, we have done just that, and layers are revealed. And these layers are composed of different materials. So in this instance, it could be sponge, jam, and cream. And they've all got different colors and properties. Now, if I've baked that cake, the sponge is very likely to be dry and brittle. If you try and fold that sponge or bend it, it's likely to crumble and break. Whereas the icing may be a bit more malleable and plastic if you try and fold it. And in a really basic analogy or a basic way, the layers in the subsurface beneath the seabed are similar. They can be composed of different materials, so for example sands, gravels and clays, and they all have different colours and different physical properties, a bit like the plasticity versus brittle nature we've just discussed. And we tend to refer to those physical properties as the geotechnical properties of those soil units. But what does that mean? Why do geological layers have different geotechnical properties? And there are many reasons behind this, but some of the main ones are highlighted here. So the origin, shape, size and mineralogy of the particles that make up that soil unit, how the soil unit was deposited there, so we then have to consider the depositional environment, and the stress history of the soil unit. So what we mean by the stress history is what has that soil experienced in its lifetime up to this point in time, basically. And so if we look at the schematic on the right, and we just look at just for this example, we can just look at that top row, for instance, you have a variety of things going on there. You have soils that are being deposited directly underneath and just in front of that ice sheet. And so they might be squashed and loaded by that ice, or they might be thrust up into the moraine. You see the mound in front of the ice. But then further afield, you move into a proglacial setting, and here we have a shallow proglacial lake or a glacial lacustrine setting. And so you may have fine sediments such as clay and silt. They might be filtering out of suspension from meltwater from that ice. And then even further afield, again, we move into an area which is influenced by periglacial weather conditions. So basically, extremely cold climate, but it's not being directly influenced by the ice itself. But just the temperature alone, those sheer low temperatures, can still have a significant impact on the properties, the geotechnical properties of those soil units there. And soils remember those. They have a memory, and so they remember it to the present day, what they've experienced. And so a fair question you might be asking, although Andrew has given us some really nice pointers at this already, is how does this relate to the UK? You know, there's obviously no ice sheets here at present, so why are we even discussing this? And the obvious answer, as Andrew said, is that we've experienced multiple glaciations over the Quaternary period. The last one of which was known in the UK anyway, as the Devensian glaciation. And this cold period started about 120,000 years ago and ended just roughly 10,000 years ago. It's estimated that the ice sheet reached its maximum extent around 20,000 years ago. And at this time, as Andrew's flagged, it's covered all of Scotland and all of Northern Ireland. The majority of northern and western England, and also the vast majority of Wales and the Republic of Ireland. It's one of a number of glaciations that we've experienced, or the UK continental shelf has experienced over the period that we refer to as the Quaternary, so the last sort of roughly 2.6 million years, and that runs right up to the present day. So I think it's hard. I always find it's quite hard to envisage what that means or what that might have looked like. And so it's always useful to think about contemporary glaciated landscapes as an analogue for what we actually can see offshore. And so in this instance, we're using an example from Iceland, and to use the famous quote by Charles Lyell, "The present is the key to the past." So we can look at this now, and we can appreciate the types of thing that Andrew has talked about from the seabed expression that we've mapped. And these might be things like medial moraines or lateral moraines in and around the margin of the ice sheet or the glacier. And then you can see in front of the glacier itself, in this instance, we have a large lake formed from meltwater, so a glacial lacustrine setting. And as I said before, that can have very fine-grained sediments settling out of suspension and creating a very different soil type to what you might see underneath and around that ice sheet. And you can see that's dammed by a terminal moraine or end moraine there, and that might have been thrust up and at the front of the ice sheet when the ice sheet extended that far, and that would therefore create a lot of faulting and folding within those deposits, which make them very complex. And we'll see some modern analogues or some examples of those in a couple of slides' time. And then further afield, we see an outwash plain there, and you can see some lovely meandering glacial-fluvial channels there. So meltwater is finding a way through that moraine and coming out of the system. And so what do those deposits look like? We're starting to think more about the engineering side, what we might encounter buried beneath the seafloor. And so you can see here some small hummocky push moraines from minor re-advances of this glacier. And you can see there's the sheer variety of class sizes within this image on the left. So everything from gravels and sands through to cobbles and large boulders. So it's a real mix, and it's very poorly sorted. And you can see the image to the right, which is a glacier being exposed, an esker being exposed at the front of the glacier here. And this esker, again, appears to be very poorly sorted and very clastic, very coarse sediment within that, mainly cobbles to boulder size class within a sort of sandy matrix, but it's very poorly sorted. And all this time we're thinking as well ahead to what this might mean for foundation design when we're planning offshore wind farms. And so here we have an outwash plain like we'd also seen in Iceland previously. And you can see again, some sections are very well sorted. So you get some really nice sorting of pure sand deposits. And then you go into more poorly sorted gravels, clays, and boulders. So it's again a real mix. And as you look vertically through that section, you can clearly see the variety. And the image to the right is an erratic, which is a boulder that is not from the indigenous rock around that area. And you can see it's not in situ. It's been transported there by a previous ice sheet. And if you can imagine that is in the subsurface and you're not aware of that, when you're trying to drive, say, a monopile that we'll touch on in a second, so a foundation for offshore wind, that's going to be a big problem and it's a big risk. So boulders are one of the things, just one of the many geo constraints and geohazards associated with these previously glaciated margins. And finally, on the examples, these are two examples of deformation in and around a previous ice sheet. So you can see here the faulting and the folding that occurred within the upper sediments, and the lower image I think is really dramatic just for showing you the sheer scale of these things. So you can see in the circle, the red circle, two figures standing on here, and you can imagine that if this is your wind farm site, if you just move from one turbine location to the next turbine location, roughly a kilometre apart, for instance, you're really not going. You can't expect to encounter exactly the same geotechnical ground conditions. They're going to be hugely varied because the ground is so chopped up and folded and faulted. So I've kind of given the game away multiple times, but why does this matter for offshore wind? Well, really, it comes down to your foundation design. So you're going to be putting that turbine on the seabed, but in the vast majority of cases, you're going to want to fix that by driving a foundation into the seabed. So I think Carbon Trust report from 2020 stated that at that point in time, around 80% of offshore wind farm developments in the UK were using the foundation design to the left here, which is a steel monopile. So you imagine a huge diameter, sort of anything from 8 to 12 meter diameter steel tube being driven into the seabed down to depths of say 30 to 40 meters beneath the seabed. You really need to understand what is within that zone of interest if you're going to make sure that your turbine is going to stay up for the life cycle of the project, so say 25-30 year life expectancy of that wind farm. Other options here include the jacket and tripod structures, which are fixed with pin piles into the seabed. And then if the ground conditions really aren't conducive to driving these sort of steel rods into the seabed, then you might have to consider a totally different design. So on the right, we have a gravity-based structure, which effectively sits on the seabed and resists overturning by sheer weight and size of the structure, but it's also aided by skirts around the perimeter or the circumference, which do penetrate the seabed, but only marginally. So this is very much designed for shallow penetration into the seabed. So this next slide is a bit dry, so I'll leave it up for a second. It's the only one without figures, I promise you. So I'll leave it up for a second just to have a quick read of, but the take-home message is that over the last decade, yes, the cost of foundations has dropped dramatically, which is very good news because it makes these projects more affordable for development. However, a statistic that I hear through working with industry quite frequently is that roughly a third of the capital expenditure for these types of projects is still covered by foundation design and installation. So that's a huge part of these multi-million-pound projects that go on understanding the ground conditions and installing foundations into them. So we really need to get that right first time round, and that's where geoscience comes in alongside geophysics and geotechnics into an integrated model. So we'll go into that now with just one or two slides, and then I'll be wrapping up and then passing on to Heather. So first port of call, I guess, is thinking about the geophysics. So the image to the top is going to take us back to thinking about our cake analogy again. So you can see here, this is a slice into the earth or into the ground beneath the seabed. You can see the sand, which is the yellow coloured very top layer. So that's your seabed, and you're looking into a slice into that. And you can see here that unlike our cake analogy on slide 2 or 3, the layers within this are not nice and uniform, and they're not laterally continuous. So this is giving us a headache because, as we saw with that example with the two gentlemen standing on the top of the exposure or outcrop, the variability here is dramatic and it's huge, and siting your wind, each turbine is going to require real understanding of that site-specific location for each individual turbine. And once you've mapped that in the sort of in the slice view, if you like, you can export your mapped surfaces as top-down plan view maps effectively. And so colleagues in the past have produced some lovely figures here that I borrowed for this presentation. And so the one on the left shows you what if you have mapped channels in the subsurface buried beneath the seabed. If you then export that layer, you might see something here, and it pops out. You can see either these, could be tunnel valleys that are produced beneath the ice sheet from pressurized water flow, or they could be sort of the meltwater channels that we'd referred to before that meander across the outwash plain. So you can see wonderful detail of a paleo landscape, but it's not just the science behind it, it's also what it means about what's filling those channels, so the infill material versus the material that they have incised into. Again, this is creating a lot of variability across your site. And finally, the image to the right, where we are looking at a similar sort of plan view that's been exported. And you can see the red colours show you the sort of thrust block moraines in the system, but you also have these black arrows showing you meandering meltwater channels, and you've got small sedimentary basins, and they may have experienced ponding of meltwater, so you may have some small lacustrine units within that. So again, just trying to re-emphasize the extreme variability across some of these locations. And so we've now looked at a bit of the geophysics that go into these models. So how about going back to the physical properties we talked about in the geology too? So we incorporate geotechnical and geological data into these models. So a quick touch on one of the major tools that we use, which is cone penetration tests, CPT. And these are a vessel offshore will push one of these rods down into the seabed, and they will push them to past the maximum extent that you'd want to install a monopile, so down to say 50 meters beneath the seabed. And this cone that you can see here is censored, so it can tell you things like the cone resistance on the tip, the sleeve friction up the side, and the pore pressure it experiences around the sensors. And this is all plotted on graphs. And just the take-home message here is that you can use these things like the squiggly blue line to work out things like the density of sand units, the shear strength in clays, and all of this goes into understanding, well, will this soil unit be conducive to installing a large monopile structure, or is it going to be not suitable for that at all, and we have to consider a completely different foundation design? So it's all about geoengineering and all about integrating that data. And so finally, we also have a borehole log here and a split vibrocore image. And so you bring the geology in too, because we need to understand that depositional environment we've talked about. If we want to understand that our geotechnical behavior or profiles from the CPT are behaving the way you'd imagine, really to understand the CPT or appreciate whether the results you're getting from the geotechnical results are correct and they make sense, you really need to understand how those soils got there and what the stress regime has been through their life cycle. And so that's another way that the geology comes in and helps to glue this model together. And so final slide on this presentation is simply the making, it just emphasize or summarize really the making of a ground model. So it's a bit like baking a cake, just wrapping it up, all the ingredients that go into your ground model. And the final, and so these key ingredients, if you like, are the geological data, which can be boreholes, core data, grab samples and photos, and all of that goes into understanding the past environment and the stress regime of those soils. The geophysical data, so we look at the cake slice and we map those layers in fine detail. And also the multi-beam that Andrew's touched on already is crucial for understanding the seabed expression as well. And finally, but last but definitely not least, is the geotechnical data, so both in situ from CPT and laboratory test data, which tell us how those soils will behave, and from that you can work out whether those soils are good or going to give you some headaches as an engineer for installing these types of structures. And so thanks very much for listening. I really appreciate your time, and I'd love to pass over to Heather now. So we've now sliding nicely down that continental slope, down the rise, and we're down at the abyssal plain, and we're going to see some lovely stuff about deep sea mapping. So I'm going to now stop sharing and hand over to Heather.
Hi there, everyone. Thanks very much. Let me just get going. Thank you very much for hanging around, and thanks very much for Gareth for introducing me. I'm going to take you on a journey, as Gareth and Andrew said, away from the UK continental shelf and into the deep sea. And we're really going to go really deep and global as well. We're going to take that global perspective. And so I'd like to tell you about Inkfish and a new project that we've got. And Inkfish is a marine research organisation dedicated to exploring the ocean. And we're in a really privileged position that we're working with a global network of specialised researchers and marine enthusiasts. And really, we're pushing the boundaries of human and scientific discovery with this project. So, of course, we're the British Geological Survey. So we're providing geological and geomorphological expertise, working with a really diverse group of biologists, oceanographers and engineers through the Inkfish Open Ocean programme. And just to put this in a bit of context, you might be surprised to know that around 75% of our oceans and seas have never been mapped using modern methods. And so volcanic seamounts, such as the ones we're flying around in the bottom left there, remain undiscovered. And large-scale features like the fracture zones that we're looking at on the right there have yet to have their sort of complexity and their full sort of structural evolution to be fully understood and imaged. So as Andrew and Gareth talked about in the previous two talks, you know, detailed maps and models of not just our continental shelves, but the deep ocean as well, are really crucial as they tell us about the evolution of our planet. They allow us to monitor change, and they help us to look after or manage these environments in the future as well. So what we have here on the right there is a slightly unusual view of our planet, but what I really wanted to sort of hammer home here is just the fact that our oceans are interconnected. And if we want to understand our oceans and how they've evolved through time and how they might change in the future, we need to explore all of it and not just stay in maybe one ocean basin or our own backyard, which of course is the North Sea and the Northeast Atlantic. So with that in mind, the Open Ocean Programme focuses on the deepest ecosystems that are found on our planet, and those are found in fracture zones, which form perpendicular to mid-ocean ridges. And mid-ocean ridges are where new crust is formed. And subduction trenches, and those are formed where the crust is being recycled. It's being pushed back down underneath an adjacent tectonic plate, down into the mantle, and it's being recycled and consumed there. But what is exciting and, in my view, unique about this project that we're working on is that we're also exploring the abyssal plains in between these features. And that's something that I think, in terms of just sheer scale of what we're trying to achieve through this program, this project is really quite remarkable. So why go deep? Over 50% of the planet lies at a depth of nearly 4,000 meters. And here we are, it's our blue planet. And this is a picture of the Pacific Ocean. And that hosts the greatest area of abyssal plain that we have. It's about 6 times the size of Australia, I think. I hope I've got that calculation right. But I mean, it just sort of embodies about why it's so important to look and explore across these deep water areas and not just stay really sort of local. And so the first Inkfish expeditions took place this summer, and we had 4 legs that went between Mexico, Hawaii and Tahiti, which sounds really, really glamorous, but the weather wasn't amazing all of the time. But we've got 3 more legs to come as well. But the aim of these expeditions is to record not only the sort of deep sea species and the biological diversity across these huge geographic areas, but we want to examine the characteristics of the seafloor and the overlying water column. And that's why we work across disciplines with partners all over the world, and mainly at the University of Western Australia. The yellow tracks in this image, that's where we've been already. So that's all along those tracks are where we've mapped and we've got data telling us about the geology of the seafloor. And the stars are where we've deployed equipment that I'll just describe in a moment. But the stars are where we've acquired information on the biological species and the water column as well. So the main workhorse is a fleet, or maybe we should call it an armada of scientific landers. So the sped up video on the right there is us launching these free fall scientific landers. So these, it's important to know, these are not connected to the ship at all. So they've got a weight underneath the white block on the top of the lander is floats. It's flotation, it's called syntactic foam. And there's a big weight underneath. And once we deploy them, they sink to the seafloor. They've got a suite of cameras and environmental sensors and water samplers and such like, that they will spend about 8 or 10 hours on the seafloor acquiring all of that data. And then at the end of that cycle, it'll release the weight and float back up to the top, and then we recover it from the sea surface. And the vessel that you can see in the bottom right picture in the background there, that's Dagon, and I'll shortly be going back out to join her for the next leg of the expedition. But on the hull of that vessel is an acoustic system that we call an echo sounder, and that's attached to the hull of the vessel, and that's what we use to map the seafloor. So in 3 months over the summer, we covered about 13,500 nautical miles. We mapped an area about the size of the UK. And what is really cool about these data is that about 75% of that coverage is completely new. So that hadn't been mapped using modern technology. So there was maybe some low resolution satellite altimetry or maybe some point data that was available before that. So really the detail, the sort of detail that has just been shown in the previous 2 talks was lacking. We couldn't tell anything in detail about the seafloor. So we're able to do that now. We've discovered previously unknown underwater mountains, like those that we're sort of zooming around in the bottom left there. But we also saw the unexpected. So on the bottom right there, that's the high fin lizardfish. And my colleague Alan Jameson at University of Western Australia tells me that this is a new depth record for that species. It's an ambush predator, so it was really remarkable that we managed to capture that footage of it at all. And it's so graceful just whenever it decides that it's not going to catch anything here. We've disturbed its sleep. It just raises its fins and just floats off the seafloor, which is really quite cool. So we've got hundreds of hours of seafloor footage. We use that not only to look at the seafloor composition from a geology point of view, but of course our biological partners are using that data to look at the species distribution and the types of fauna that live at these depths. And we work with oceanographers who look at the CTD data. CTD stands for conductivity, temperature and depth, and the amount of data that we've got going from the sea surface down to the sea floor is equivalent to about 90 times the height of Everest. So we've got a lot of data that our partners are churning through, and we're already seeing some really interesting insights into the water masses that overlie these abyssal plains. And so just an example of some of the seascapes that we imaged. So the dominant sort of shape of the seafloor that we did come across the abyssal plain was, as we expected, it's something called a seafloor fabric. And that's a record of how the ocean crust was created at the mid-ocean ridge. So tens of millions of years ago, as that oceanic crust was being formed, that record is still preserved on the shape of the seafloor. We came across volcanoes of varying sizes and morphology. Like in this example here, we've got the musicians' seamounts, and it's worth, if you've got a little bit of time after the talk, to go onto Wikipedia and have a little look at how these are named. They're all named after composers, but they lie to the north of Hawaii, and they're pretty cool. But we also see ridges, and the Murray fracture zone is labelled there in the sort of top left of the image there. But each of these geological features have a distinctive composition, like the polymetallic nodules, which we see if you can zoom in on the well, not zoom in, if you can focus on the picture of the red prawns, you can see that the seafloor is covered in these polymetallic nodules. And then on the bottom left there, the two images show a sort of brown sediment covered seafloor. And that's a sort of clay-rich seafloor, but we see the composition of the seafloor change as we move across the abyssal plain, especially when we go sort of north and south across the abyssal plain. And so just a couple more examples. On the left there, we've got the Murray fracture zone, which was discovered in 1954 by a number of American research vessels. But again, it's this dominant seafloor fabric that creates these parallel ridges, and these can be up to 300 meters in height, and we've got bedrock cropping out at seafloor. Some of it's got a sort of sediment drape on it as well, and that's really interesting to us. But what I think is really interesting about this image here is that you can see that the tops of the ridges are just bent by the Murray fracture zone there, so that the impact of movement along that fracture zone is creating change along that fabric. But the structure of the fracture zone itself is revealed. So it's not just one single fracture, you've got multiple strands and you've got movement along those. And each strand of the Murray fracture zone is slightly different. So it's had a slightly different evolution, and we're starting to unpick that story now. Interestingly, from some of my biological colleagues, is that in places, the water depth in these fracture zones exceeds 6,000 meters, which is a bit of an interesting sort of biological control on some of the pressure adaptations that various species that we see down there have to compensate for in order to exist. So that's firmly our colleagues' interests, but I find it quite interesting to work cross-discipline. On the right there, what's really cool is that a number of these volcanic knolls, which are features that are less than 1,000 meters high, and the seamounts, which are bigger features, so they are bigger than 1,000 meters high, a lot of them have got submarine landslides on their flanks. So we can see the evolution through time and the life cycle of these seamounts and these knolls as is being revealed by our new mapping. So the post-formation evolution of these features is something that we're doing active research in just now. And of course, as soon as we see a submarine landslide, little alarm bells go on, and we start to think about geohazards. Are these, fairly benign features, or are they something that has an impact in terms of tsunami potential? But just to kind of give you a little flavour for some of the video, we've got a happy prawn there in the bottom left. But if you can take your eyes off the really happy prawn who's feasting on some mackerel there and look at the seafloor beyond, and again, we're starting to see we've got some crust, some dark bedrock cropping out at seafloor, volcanic bedrock, but we can also see polymetallic nodules as well. And in between all that is clay-rich sediments. What is interesting about this project is that we've also got access to a crude submersible. And the video on the top left there is an example from the Java Trench, which is somewhere that we've visited before. And what is really quite unique about using a crude vehicle like that, it's the equivalent of walking along a cliff section on the beach or doing field work in the Northwest Highlands looking at the thrust faults and stuff up there. It's the ability to direct in situ geological observations of the seafloor, which is just as we would do onshore if we were making a new geological map onshore. So the example from the Java Trench there, you can see all those bright colours, those bright oranges and yellows. And that's evidence of fluid circulation in the rock mass. So that fluid is being taken deep down into the crust, it's warming up a little bit, it's dissolving lots of lovely minerals. And as it's then being recycled out through the surface of the rocks exposed at seafloor, it's creating a unique environment for bacteria and other things to live off, which is what the bright colours are that we're seeing. And the example on the right there are using the stills camera, and that's work that we've been doing offshore Western Australia between about 2,000 and 6,000 metres water depth. And you can see that the geodiversity of the sea floor is really quite striking. And being able to actually acquire data and what we call ground truth, which is something that both Andrew and Gareth talked about, as well as what we, and that's something that we do on the continental shelf. We do the exact same thing in the deep sea. Water depth isn't necessarily what we worry about. We just want to be able to do the exact same sort of robust scientific investigation, just as we do on the continental shelf as we do in the deep sea. And so just some final thoughts from me. I really hope that I've managed to give you a flavour of the cutting edge research that we're undertaking as part of this collaborative, unique, interdisciplinary project. And just to sort of highlight again that I think the scale of this and the ability to keep going back and undertake multiple expeditions to investigate these features and to really drill down and get to the nitty-gritty of the research and the big questions that we want to ask and answer with these data is just unprecedented as far as I know. I hope I've given you a flavour of the ongoing work. This is all very hot off the press. We were just in the field during the summer, and we've got another 3 trans-Pacific transits to complete in the coming months. But we're looking at, research questions around seabed sediment composition and the variation across these geographic areas, the seafloor geomorphology and geohazards, just to name a few, but also working across disciplines. So marrying up data from the geological perspective with the biological and the overlying oceanography as well. But really, this is just the beginning. So perhaps in the future, we'll get the opportunity to hold another webinar to give you an update. But over the next year or so, we're heading to the Philippine, Tonga and the South Orkney trenches. And this is really just the beginning. This is a really amazing project that we're really privileged to be a part of, and just watch this space for some more excellent research and images to come out. So thanks very much, and I'll hand back to Andrew now. Thank you.
Thank you, Heather, and thank you very much, Gareth. So we've heard about our new seabed geology mapping program offshore around the UK. We've also heard about now how we can slice through the geology and the continental shelf like a cake, like a tasty cake cooked by Gareth, and see the layers inside and what those layers mean for putting foundations into the subsurface. And as we've also heard from Heather about how we're exploring totally new landscapes through in the deep ocean through this Inkfish program. So it's now time to take questions. I shall hand over to John Paul from our comms team, and John Paul's been keeping an eye on the questions. So over to you, JP.
Hi, everyone. And first of all, thank you very much to yourself, Andrew, Heather, and Gareth. I hope everyone who tuned in enjoyed it as much as I did. So the first question, this is directed at Gareth. The question asks, presumably laying cables between the pylons is a geological challenge as well?
Yeah, completely. Yeah, good point. I mean, what I must probably emphasize is that in the sort of 12 to 15 minutes there, I very much focused on the foundation design, but you're absolutely spot on. So you'll use a different type of geophysics to look at cables. So because if you think about it, your zone of interest changes dramatically. So as you rightly say, you want to understand the ground conditions in the upper 5 meters between the turbines. And they're called the array cables. And then also you want to understand the upper 5 meters from the site right into what we call landfall. So that's the coastline, because you need to get that energy back into the national grid for us all to use. And so effectively, you need that export cable to run the energy back onshore. So you have your deeper geophysics for your foundation design, and then you have higher resolution but lower penetration. So you get like much more detail, but just in the upper 5 to 10 meters for your cables. And you might just use, Andrew showed a nice example of vibrocore equipment on deck. And so you might use vibrocores to ground truth that geophysics, and that's only going to collect a barrel of, as Andrew says, maximum 6 meters of recovery. Whereas when you're looking at your foundation design, you're going to be looking at deep CPTs down to 50 or 70 meters, maybe even, and you're going to be looking at geophysics that gets you deeper penetration into the seabed. But yeah, absolutely bang on. You need to consider the cables between the turbines and also the cable to get the energy from your wind farm into the national grid. So yeah, good point. And I'm glad you gave me the opportunity to say that. So thanks very much for asking a great question. Thank you.
Great, thank you, Gareth. So the next one is for yourself, Andrew. Is there any international collaboration between geological surveys so the mapping will not be constrained by international boundaries?
Yep, very good question as well. So BGS, we're engaged in 2 programs. So there's the EMODNet program, which says for European Marine Observation and Data Network. So we put our mapping data up on there, some of our mapping data up there, and make sure it's in a format that can be consistent with other European surveys. So it's so there's like a seamless map data in that platform. But we're also part of the Geological Service for Europe, where we're looking at all the kind of geological surveys across Europe, are looking at kind of consistency and harmonization for how we map, for example, areas suitable for wind farm siting. So yeah, definitely we need to get rid of these international boundaries, because the geology doesn't stop at these boundaries.
It's a really good point. Like you say, yeah, the mapping doesn't necessarily recognize international boundaries. It goes beyond that. So Heather, one for you here. And this was talking about the Inkfish project. The area off southeast Mexico is a big target for seafloor mining of things like manganese nodules. Is seafloor mining a scientific objective of the project?
Yeah, thanks. Of course, it's a hot topic of conversation. There are frequent news articles about seafloor mining. We are solely interested in scientific exploration and to look at the research. So our partners and I, we are independent, and we provide sort of scientifically robust information around all of the environments of the seafloor. And if we happen to come across nodules, that's very interesting to us, but we are not affiliated or anything to do with seafloor mining. And if anything, the information that we gather can be used for future environmental impact assessments in whatever direction that industry happens to go.
Brilliant. Thank you, Heather. So back to yourself, Andrew. This question asks, have you been able to reconcile stratigraphy from onshore to offshore?
Oh, this is a good question. It's a challenge. They've been your different data sets, you're starting from different starting points. One thing that we do, we can see, when we look at the geomorphology, we can see a lot more detail in the offshore. It's amazing kind of geomorphology that we see when we're looking at kind of mapping bedrock. So we might want onshore, we might be able to map bedrock to formation and bed level, whereas offshore we're not able to kind of ground truth it so much. So we're looking, we might be looking at group level, or even even beyond that. So when we're kind of characterizing or dividing up the bedrock, it's not as easy in places offshore, but what we are able to see is a lot more in terms of the structural geology and the fractures and faults within the bedrock from the multibeam data. I will open that up to my colleagues if they have anything to add about some of the wider sort of stratigraphy, maybe from the cores and things like that as well.
I mean, from
Gareth, any further comment on that?
I mean, I can just say from an applied sense that we have looked at we have looked at extrapolating or linking coastal exposures for certain till deposits, for instance, with what we see in the offshore domain, and it gives you that, as you say, laterally continuous stratigraphy, because obviously, again, a bit like the national borders you touched on there, you know, an ice sheet doesn't stop onshore and start again offshore, it's all continuous. And so yeah, we have definitely looked at continuity from onshore to offshore from an applied sense, and I guess we'll continue to do that going forward. Yeah, sorry Heather, I cut you off too.
No, not at all. I think just to add, we always called it the white ribbon, was that little bit that we couldn't quite get data in to seamlessly marry the onshore and the offshore. Of course, technology's evolved and we're bridging that white ribbon now. But I think traditionally it was always just a little bit difficult. There was different naming conventions that we're still getting to grips with now and rectifying. But also it is in part just an element of scale, that whenever you've got sort of your offshore ground truthing or sort of, you know, disparate cores, you know, with, you know, tens of kilometers round about them, between them even, and then trying to reconcile that with what we see onshore with a lot more information. And, you know, people have been working onshore for hundreds of years, you know, the great geologists of the past, you know, have been documenting the various members and formations for a long time. So it's just that we're not playing catch up, but it's we're just sort of bringing together two slightly different ways of gathering information. But we're doing that just now, and the offshore Yorkshire data set that Andrew presented earlier, and the Anglesey and the East Anglia data, check out the offshore geo index. That's bridging that gap now, so we'll be able to do a bit more work at marrying on the onshore and the offshore.
Yeah, no, it's just to add again, it's hugely important. It's 100% something that we want to do, because there's a lot, you know, that kind of coastal zone. It's so dynamic, and there's so much going on there in terms of processes, but also in terms of, you know, where we want to develop in terms of the infrastructure in the coastal zone, or we have, you know, landfall sites for cables and things like that. So we do need to make sure that we have good, seamless onshore, offshore mapping, and it's something that we want to push ahead with in BGS. And there's loads of opportunities now with our new, you know, new onshore mapping program as well. So we want, you know, within BGS, we want to make sure that we're getting our marine geoscientists out in the field with the onshore geologists, and vice versa, give the onshore geologists opportunities to look at the marine geoscience. So yeah, definitely good collaboration opportunities in that one.
Great, thank you all. A really nice answer to a really good question. Just to say that the questions now coming in thick and fast. We'll do our very best to get through as many as we can in the next half an hour. But any we don't manage to get to, we will do our best to answer them offline. And when we release a recording, probably in about a week's time, we'll try and have a document with answers to your questions. So Gareth, this next one's for yourself. And I think it probably relates to the question we've just had. How are onshore and offshore engineering geology surveys similar but also different?
Oh, that's a. Do you know, that's actually really tough if we're thinking about like an onshore wind development, for instance. I've not personally been involved. I've been a marine geoscientist for all my career, really, with BGS. So I'm not too aware of the techniques they use, but how are onshore? I'd probably suggest that the geophysics will probably play a larger role, I guess, in the offshore environment. You know, that seismostratigraphic framework or model that we discussed there. I think that's going to be more widely used, whereas onshore, I think you're really going to be looking more at borehole recovery and lab testing, I'd imagine, for your foundation design. A thing I've never considered before, actually, until this question's asked now, which is why it's great, is what the difference in foundation design is. I don't know whether the zone of interest changes as well, and something I guess to look into. But thanks for asking, and I'm afraid I have to give you that bit of a wishy-washy answer there, because I've not actually worked with onshore infrastructure. So
I would expect from the onshore, it basically would be, you know, there'd be a lot more trial pitting. Again, sort of shallow boreholes, new ground penetrating radar, and it just the ability to basically walk over the land.
Yes.
You know, with trial pitting, you get that opportunity to actually, you are taking a physical slice out of the out of the ground, as opposed to offshore, where you're taking a slice with the seismic. But again, lots of similarities as well. One is to kind of build up that model, and again, sort of key things of interest. So again, offshore, onshore wind farms, you definitely want to know if there's peat there, the thickness of that peat. I guess you'd be looking for organics and peats and things like that offshore, too, because they would be something to flag.
Yeah, I think I think that's probably in a nutshell, isn't it? That they at the end of the day, they probably use similar techniques, just in different ways. You'll probably still be integrating geophysics, geotechnics, and geology as the three sort of pillars, if you like, for your ground model development, whether you're onshore or offshore. So it's kind of transferable skills, I guess, because we know from colleagues that have worked with GPR onshore that, when you're looking at those slices of seismic, if you like, then similar sort of skills are needed to interpret it. So yeah, I think that's a good point, Andrew.
Great, thank you. So this next question is for Heather. Great talks, everyone. Thank you. The question starts. How long does it take for the robot to go down to the seafloor for deep sea exploration?
Yeah, great question. It really depends on water depth. So it could take anything from maybe half an hour, to get down to sort of maybe 2,000-3,000 meters for the landers and things. But if we're working in some of the deepest trenches of the world, that will actually be 2, maybe 3 hours for the landers and stuff to get down. So then you've really got to do a bit of planning. You've got to think about your battery management to make sure you've got enough power to keep the systems running for all of that time, and also to allow enough time on the sea floor for the equipment to actually record something that's scientifically meaningful. So it varies with water depth from maybe 40 minutes or so, an hour maybe, on the examples that I was showing across the abyssal plains, but it's a bit longer whenever we're dealing with the really deep stuff.
Brilliant. Thank you, Heather. So this is a question I'll open up to all three of you. So the question asks, how do you deal with the salt content of sands and gravel from the seabed? Does that impact any of the technology or the measurements or the processes that you try and use to map or study the geology under the sea? Does the salt content have any bearing?
I want to say that. To be honest, it's not something in I'm too familiar with. I guess if you're talking about kind of extraction of sands and gravels, I guess that would be one thing to be considered. But again, outside my kind of area of knowledge with that one, I know, for example, from onshore surveys, if you're taking, for example, ground penetrating radar over salt, or getting close to the coastline where there's salt water within sort of beach sands and things like that, it won't work because GPR doesn't work when in saltwater saturated sediments. But I will see if anyone else has got a comment, more informative comment than me on that one.
I mean, this is maybe a bit left field because the question itself is looking very much from the seabed, but there is always one of the main geohazards or geoconstraints for infrastructure offshore that we will always consider would be salt diapirism. The salt content within the subsurface, so where you get halites and things like that, and they are problematic ground conditions for offshore construction. With major loading, salt can behave in a more plastic fashion, for instance, and you get compressible ground. So yeah, salt's something that needs to be mapped, and you can do that through the multiple techniques that we've discussed so far. So we can map salt doming within geophysics. That's one of the main ways that we would do that. I don't know if that question's directly asking that, and so, but I just thought I'd throw that in there because it's interesting to think about geoconstraints and geohazards, not just the big dramatic landslides and things which are so cool, like Heather showed, but also some of the more lesser well-known geohazards out there, and salt content within the subsurface is actually one of them. Yeah. Don't know if Heather wants to chip in or whether she's like, no, I'm done.
Thank you very much, both. And for the person that asked that question, if we haven't answered it and you want to clarify, please do come up with a follow-up question in the chat and the Q&A. Sorry. So actually, going back to yourself, Gareth, this next question says, What's your opinion on the synthetic CPTs and how they represent or don't represent geological complexity?
Really good question. And this is obviously someone that's working in this field because it's very topical. So for anyone else out there, we've looked at CPT in my presentation where you drive a cone into the ground. And the concept of synthetic CPT is where you can train your model so that if you moved a CPT point, it would give you an artificial profile of how it would expect that soil to behave, like what that sort of squiggly line would look like, which would then allow you to move your turbine, what we call microsighting. So you move from one location and you bump it over to another location that's quite close, but without having to drill a new CPT, because your model will tell you, well, if you move it here, your ground conditions are likely to react like this in a geotechnical sense. So that's a concept of synthetic CPT. And I think it is such a valuable resource that's being explored just now, and it's continuing to be explored. There's some fantastic companies in the private sector doing this, and there's some universities looking into this too with PhDs. And I think my personal opinion, and this is mine, is that it needs to be explored, because one of the main barriers to more green energy from offshore is simply cost. And so if we can drive down the cost of the number of CPT we need to collect, then we're effectively enabling the industry to be able to progress these types of major renewable projects. There's some fantastic evidence out there that this can work in a good sense. I won't name names of organizations because we're impartial, no favoritism, but in the Dutch sector, there's been a webinar that's in the public domain where the contractors and consultants that undertook that modelling showed a really thorough example of how it's done and what it looks like. And all I can say is I'm in favour of further research into this. I think the question there, which is in part of that question around the complexity, is probably the big thing that needs further exploring. It's not to say it doesn't work by any means, but I think the crux of it is that further research into how we develop synthetic CPT or synthetic profiles when you have a lot of lateral and vertical variability. That's the big question mark around it just now. But we know contacts and partners who are looking at that exact question right now. So it's only a good thing. So I'm in favour. I'm definitely in favour. I don't know why I waffled so much. I should have just said that they're great. But yeah.
Thanks very much, Gareth. Okay, this next question is going back to the deep sea to Heather. Could any of these new undersea mapping techniques be used to further understanding of the ocean floor and what the marine environments during the Mesozoic and Paleozoic eras looked like?
Yeah, wow, gosh, great question. So really this question is about paleogeographic reconstructions. So that's trying to picture how, the continents or what sea level was doing in time slices in the past. So you mentioned the Mesozoic and the Paleozoic specifically. As far as the deep ocean is concerned, then yes, exactly. Once we get more and more data coming in, then we'll be able to sort of dial back the clock and see how the ocean floor has evolved over time and during the sort of eras that you're talking about as well. But we also work with European partners, and this links to an earlier question that was directed at Andrew as well. We work across borders with partners throughout Europe, looking at paleogeographic reconstructions over the last sort of million years or so. And that's related to sort of submerged landscapes and maybe looking at how early humans sort of, walked across land masses and stuff during times of fluctuating sea level and such like. So we work across different geological timescales, but also different areas, not just domestically and European wide, but also looking globally as well. So we will be looking at these paleogeographic reconstructions.
Brilliant. Thank you very much, Heather. Andrew, I think at the start of your talk, you invited suggestions or requests to map parts of offshore UK. And so there are a couple of questions here. There was a suggestion for Aberdeenshire and also a question if there's any plans to map the Solway, Morecambe Bay area as well.
Yes, definitely. Like we basically want to map it all. Yeah, it's a question of kind of staff capacity and things like that. So we're getting some more staff in, and we're definitely wanting to up our level of the amount of mapping they're able to do. Offshore Aberdeen, kind of Aberdeenshire area, definitely is in the kind of target for the next 2 to 3 years. There's a lot going on there, and both in terms of the applied drivers, but also in terms of some fantastic science in terms of ice sheet processes and deglaciation story in that area. So there's a lot of good reasons to map that area, and we'll probably move down into that after we finish the Murray Firth. And then Morecambe Bay, there's less data at the moment available, less high resolution multi-beam data at the moment available in that kind of Eastern Irish Sea area. More is coming online soon, so we'll keep an eye on when and what data comes out and when, and definitely you get going in that too. It would probably be one that would take a little bit longer to get into that area, but off Aberdeenshire is in the targets for the next couple of years.
Brilliant. And actually, another question for yourself, Andrew, because I think you touched on it in your talk. But the question here asks, how accessible are these data sets? Could some of the audience members here download borehole data, for example?
Yeah, definitely. So if you go to the Offshore Geo Index, you can download scans from boreholes. You can download grab samples. Lots of information there. You can download some of the map layers. Some of the map layers are licensed. Some of the map layers can be downloaded. So I need to go back and look specifically which one is which. But yeah, there's loads of information available for download from the Offshore Geo Index.
And it's really easy to access because I just did that for my own sort of work as well.
Yeah. I use it all the time actually for our own data too.
There was a couple of questions that came in about whether we will release a recording of this. And again, I think we mentioned earlier, but we will. So anyone who's registered for this webinar, whether they've attended or not, we will send a recording so you can watch back or revisit certain sections. And we'll also try to include some links off to the Geo Index, etc. So yeah, just so you can access them as easily as possible. There's a question here that I'll open up to the three panelists. Does BGS use satellite data in its research, and how often, let's say in percentage, you access such data? Is that something that's used for offshore?
Yeah, we use it.
Oh, sorry, Andrew, you go first.
Yeah, definitely we use it a lot onshore for sure. It's used in it's like sort of again aerial imagery or digital terrain models or INSAR. So we definitely use it onshore. Offshore, probably around the coastline, around the UK, the water is quite murky in places, so it's less. You're not going to be able to pick out as much, but in areas where there's very clear water, you can use it also for getting some of the water depth and some of the bathymetry from satellite data. Gareth, sorry, you were going to go on and speak on that one too.
Well, I was just going to say, yeah, we've got those colleagues who have been working in the shallow marine, at least, to use satellite data to try and analyze really how effective it is as a proxy for multi-beam bathymetry, for instance. Because I mean, if you want to look at sediment wave migration in the nearshore zone or something like that, if it's going to be quite costly, as we know, to go and repeat survey. So you go out 1 month, do a multi-beam survey, you come back and analyze it, and then you effectively build up a model over time with overlying bathymetry. But if you can just take a snapshot every time a satellite passes over and it shows you changes in seabed elevation, then that's a really effective, cost-effective way of assessing that, which is very valuable for many things, including sort of navigational risk for vessels in the nearshore zone, through to subsea cables, as we've touched on. If they're buried but then the sediments are moving and exposing them, then they're at risk from external forces such as anchor impacts from vessels. So yeah, we have got colleagues who have looked at and continue to look at satellite image specifically for the nearshore zone anyway.
Yeah, coastal change as well is definitely our coastal team would be looking at that.
Yep. In the deep sea, satellite altimetry data is used quite routinely where we don't have actual kind of surveyed data used, acquired using vessels, like the examples that I was showing. That being said, satellite altimetry, although it's much coarser resolution, so you maybe only have sort of one data point in a sort of kilometre by a kilometre cell, that still gives you sort of a lot of information about the sort of shape of the seafloor, but at a sort of broader sort of scale. And we've certainly used that for past studies. So if you go into the BGS website and into the news articles, you can filter by marine articles. And we've got, I think, at least 2 articles in there where we've used this satellite altimetry data to look at sort of bigger geographic areas and looking at the features that are there. The sort of massive geomorphology of the seafloor, including subduction trenches, seamounts, plateaus, and such like. So I can think of one that we did in Northwest Pacific, for example. So they're really, really useful data sets, and they can certainly guide and inform where we're going in the future and where we maybe want to spend more survey effort going to investigate.
Brilliant. Thank you very much. So we're into the last 10 minutes, so I'll try and pick a variety, because there's some themes that are coming through, and we've actually got more questions now than we had at the start. So it's great that so many people are engaged. Fantastic questions, and we'll do our best. But like I say, we will answer these offline after the talk. So this question, I'll start with yourself, Gareth, but I'm sure Andrew and Heather, you might want to chip in as well. Can you use remote sensing for the intertidal zone? I know this has been done in the Republic of Ireland for archaeology.
Yeah, I mean, yeah, I guess I can kick it off, but I think both Andrew and Heather will also have thoughts on this. So, I mean, we use LiDAR routinely, as Andrew said, LiDAR for that intertidal zone. As Heather touched on, traditionally that white ribbon zone around the sort of intertidal near zone has always been a problem for data collection. But going forward, or now we have new techniques such as LiDAR, we're able to stitch that together with the multi-beam and create that seamless topographic survey. One of the other sort of techniques that's been looked into is passive acoustic monitoring. So Trimino, our colleagues in the nearshore zone, have used that, and that's where you basically have it's basically a geophysical sensor, but it doesn't use a source, so like a noise emission. It uses the background noise of waves crashing on the beach and things to generate a source, and you can then get a signal that might show you sediment thickness in the nearshore zone and the intertidal zone. And so you can actually do that at low tide as a survey geologist onshore. So we use geophysics and remote sensing as a sort of an amazing stopgap, or an amazing tool for stitching together our onshore data with offshore data. But yeah, I don't know if the other guys have any thoughts on that too.
No, I think you summed it up nicely, Gareth.
Great, thank you, Gareth. So this is another question that I'll put to all, but I'll go maybe to Andrew this time to start off. And there's a couple of questions along this as a theme. So do you have access to offshore commercial 3D seismic surveys that are now public domain? Have any of these seismic companies come forward with their bathymetric data to assist with the program? And I'll follow up, because there was another similar question, if there's any requirement for, I guess, commercial companies that are producing or recording similar data to provide this to the Geological Survey.
Yes, we do use that data. We are being sort of given access to that data. Some of the data has been uploaded, for example, to the NSTA, North Sea Transition Authority. But there's also data we're being provided for by sort of on wind farm projects, which is massive for us, because it really helps us. We're really wanting to develop this regional geological knowledge, this geological expertise, and to develop kind of wider regional understanding that can then be put into new updated maps and models that kind of supports a wide variety of users. So having that data is hugely beneficial for us, because it's massively valuable data, and a kind of a massive step forward from some of the legacy data that we've had previously. I know that Gareth and Heather will both have something to add on that.
Yeah, so we've had a number of projects, both currently ongoing, but also in the past, looking at some of these 3D sort of what we call sort of merged surveys as well. So looking at really large geographic areas, in particular in the North Sea and in the Faroe Shetland Channel. We had a great project just recently with the University of Manchester and Queen's and Belfast, looking at the Quaternary. So a record of the last 2.5 million years of paleoclimate change that is preserved in sort of just over 1,000 meters of sediment in the North Sea. So using exactly as the person has asked there, these 3D released seismic datasets. Thinking about, it mentions bathymetry data as well. There's a lot of vessels actually, when they're transiting to and from site, don't tend to switch on their bathymetric systems, so that data isn't really around. There's something called OLEX that was that's unprocessed sort of bathymetric data that's uploaded by vessels that we've used in the past as well. But what is really cool about some of these 3D seismic surveys is that you can reprocess it for what's called the first return. And that's the sort of near seabed return. And we don't want to say pioneered, but we certainly did some of the earlier work in that in the 90s. So before my time at BGS, but only just. Looking at the seafloor in the Faroe Shetland Channel, for example, and we saw polygonal fault systems cropping out on the seafloor, which are you know, they literally look like giant polygons all over the seafloor, this sort of lattice work of features. You could see where the ice had got to, that Andrew talked about in his talk as well, and Gareth too. You can see that got to the shelf break in the Faroe Shetland Channel, and then all of the downslope processes. So all of that material that the ice had carried to the shelf break getting cast down the slope and into the bottom of the Faroe Shetland Channel. So that told us a lot about the extent of that ice sheet at that time, because it was completely unknown. So we work with a lot of partners. We do use these sort of data, and I realise I've done a very long-winded answer, but it's because we're all really interested in the data, and it's a phenomenal data set that we're able to work with. But as Andrew says, you know, we're recruiting heavily just now because there's so much data. It's all so cool, and we don't have enough time to work it all up. So apply for a job.
So much to do, not enough people. I think, yeah, the last thing I would add, I think you guys have totally covered this, but I think that, yeah, a shout out really needs to go to the developers now, because there's a big sea change, if you excuse the pun, in which was definitely intended. The developers are now really seeing the value in the science behind you know, the data that they're collecting, and they're starting to share it with us because they can see the merit in allowing or facilitating us to update our regional models, and that includes, you know, 3D seismic, and it includes multi-beam for the seabed. So we really, you know, as a survey, we're really grateful to the private sector for working with us on these types of projects and making these fantastic data available to us. And, you know, we couldn't really do it without their help. So I think it's important to acknowledge the role that they play in you know, everything that we do for seabed to subseabed mapping, basically. So just wanted to chuck that in there.
Great, thank you very much. Okay, I'm going to finish with one more question, and then I'm going to ask a question of my own, if I can be cheeky and sneak one in at the end. So the last question to yourself, Gareth, is surveying only required for pre-construction, or would this also be useful for decommissioning as well?
Yeah, do you know what? That's a great question, because there are different phases to these projects, as you can imagine. In a typical sort of pre-construction phase, you will have typically three surveys. You'd have a reconnaissance survey where you might collect, you know, anything is like just 8 boreholes and then 15, 20 CPTs and some seismic lines, and you'll build your preliminary model, and then you go to the intermediate survey phase, and you'll have a final ground model phase. So you'll have your pre-construction surveys, as this question points out, but something even decommissioning, it's really important to acknowledge that repeat surveys with multi-beam, for instance, will happen all the time through the 30-year life cycle of that project, because what they need to understand is, as we've already touched on, the seabed can be very mobile, and they need to know that nothing has changed at their site and their structures, in particular the subsea cables that are buried in just, you know, 1 to 2 meters of sediment or below the seabed. They need to know that they've remained buried and that there's no risk that they're exposed to a ship's anchor to tear them up, because if you break a cable, you're talking, you know, in excess of 5 million to repair one cable, so it's a big cost. So yeah, I think surveys actually happen all through that 30-year life cycle, including decommissioning. From the decommissioning aspect. I think one of the big interests is actually on the sort of the biological benthic ecology aspect as well. So there's many reasons to survey, and the surveys are not just pre-construction. I think mainly from a subsurface modeling perspective, our role is pre-construction for sure. But from a seabed sediment mobility perspective, you know, multi-beams collected routinely throughout the 30-year life cycle of an offshore wind farm, and as this question points out, also for decommissioning purposes too. So yeah, good question. Good to point out or to highlight that, yeah, it's definitely not just a one-off sort of survey at the start and then job's done. It's a real commitment for the lifespan of the project, really.
Thank you very much, Gareth. So the question I would like to ask each of you in turn is, I think you've done a really good job of giving everyone in this talk an idea of the amazing data, the research that's going on, and what we're learning, the knowledge we're getting about the seafloor. But I think you've also given us a taste of how relatively unexplored the seafloor is. Even on our continental shelf, we are mapping it in greater detail than ever before. So there's that sense of exploration. And in some cases, in some of the areas that Heather's touched on, you know, it might be being mapped for the first time. So my question to each of you is, if you could have your wish and you could research any part of the ocean floor, any part of the the geology underneath the waves, what area would really excite you, and what would you hope to get a chance to work on in the future? So I'm going to go to Andrew, because I feel like he's not said anything for a while. So go to Andrew first.
Oh, thanks, JP. You put me on the spot. That's a good question. So lots of things. To pin down one, I'm a glacial geologist at heart. That's my bag. So I would definitely be looking at ice sheet processes, ice streaming. You know, in the UK continental shelf, we've actually got some of the best record for that. We've got a whole imprint for you know, the collapse of what was a marine-based ice sheet in the end. So I would be researching that, just getting more data. You know, we're so lucky with the data that we're getting, but then also go to some quite cool places to research the same stuff. You know, get a chance to get to Antarctica or Greenland. Antarctica, I'm looking at Heather there. So yeah, that's my my view on that one.
Thanks, Andrew. Good answer. Okay, Heather, over to you next.
Yeah, okay, crikey. That is a great question. I think actually I am going to go to Antarctica with this one. I'm going to the South Orkney and the South Sandwich Trenches. So we managed to get to the South Sandwich Trench briefly a couple of years ago. But these trenches are cryogenic, so they're actually sub-zero at their bottom, which is a really interesting sort of phenomenon. But also the fact that, especially South Orkney, for example, we're going to see, like Andrew's just talked about, some of the glacial processes being preserved right out across the continental shelf. We're going to be able to do a full, you know, source to sink study across the continental shelf, these massive sort of trough mouth fans, processes going from the slope down into hadal depths into these cryogenic environments, and just here be dragons. It's going to be awesome. That's where I would want to go.
And thank you, Heather. And then finally, Gareth.
Do you know what, guys? It's kind of embarrassing to say, but I'm so boring. I'm so boring. I literally love the work I do right now, and where I am, and yes, it's so dull. I think the thing I love the most, and I'd love to research more and continue to look at, is the effects of that really cold climate in, you know, periglacial settings. So not necessarily like Andrew's talking about, you know, the subglacial processes, and you know, I'd really like to look more at, you know, the influence this has on soil properties, and from an engineering perspective, what this does to bedrock. So bedrock is exposed and frozen and unfrozen multiple times for, you know, hundreds of years, you know, and the effects this has on that bedrock is it can do multiple things. And we've got amazing colleagues in the BGS team who are looking at, you know, the effects on chalk just now, for instance, from an applied sense. And it's just fascinating the work they're doing, and we're looking at a similar thing for another site with mudstone, and it really just shows you the power of ice and what it can do to these, what you'd imagine are, you know, they're millions, hundreds of millions of years old rocks, but they can be turned to effectively clay or putty due to this freezing and thawing process. And that blows my mind in a really geeky engineer way. I'm like, that's just incredible. And so super lucky to work with that kind of data and the people that we work with. So you know what, quite happy doing what I'm doing where I am. It's all good. So yeah, lucky, very lucky in that sense. Yeah.
Is that answer anything to do with the fact your boss is listening, Gareth? Is that
Andrew heard all that, right? He was listening, wasn't he? Okay, good. Yeah.
Okay, listen, I just wanted to say one more massive thank you to our three speakers tonight. I think it was an excellent presentation, a lot of great questions, great answers. I'd like to thank everyone who registered for the talk. The fact that it was so well supported. This is the best response we've had to webinars so far. And it's definitely given us the incentive to do more talks like these. So we will try and arrange one for the new year, probably around February time. And also try and at some point in the future do a follow-up with members of the Marine team to see how work's progressing on the various projects that we've got ongoing. So is there any final words from any of the panelists?
No, just thank you very much for joining us, for everyone sticking with us for an hour and a half, and it looks like we still got good numbers here. So thank you for listening.
Absolutely.
Brilliant. Lovely. Have a lovely evening, everyone, and thank you very much.
Okay, thanks.
Excellent.
Bye now.
Thanks, everyone. See you later.
Cheers.
Bye-bye.
Bye-bye.
Bye.